I'm Rihanna Rousseau. I manage the XRF and ICP-MS unit. Before we start, I would like to introduce the rest of my team. So in charge of XRF and mineral separation is Mareli. In charge of solutions, ICP and CH&S is Shanae. And our mineral separation wizard is Herschel.
Welcome to the XRF Spectrometry course. During this presentation, we will cover the basic concepts of understanding XRF spectrometry. We will start with an introduction into the physical properties of X-rays and how these properties form the core principles of XRF spectrometry. Once the physics behind the XRF analysis is covered, we will investigate all the different components of the spectrometer. Each component has to function under specific parameters to provide the best analytical results. Sample preparation will be briefly discussed. More details into this topic can be found in our sample prep course for ICP and XRF analysis. After the instrumentation parameters are discussed, we will end the session with calibration setup and analysis. XRF stands for X-ray fluorescence. Simple to state that X-rays form the core of XRF spectrometry. X-rays are produced by the deceleration of high-energy electrons and by electron transitions in the inner orbitals of atoms. So let's look at a few important properties of X-rays and review this definition. X-rays propagate in straight lines. They are undetectable by humans as they are invisible and we can't hear, taste, smell or feel them in our surroundings. X-rays can be transmitted, reflected, diffracted, scattered or undergo photoelectric absorption when striking matter. When interaction with matter occurs in these various manners, the results can produce and emit photoelectrons, Auger electrons, spectral lines, and continuum radiation. The last two mentioned properties form the core of XRF spectrometry. X-rays are part of the electromagnetic spectrum, where it can be expressed as wavelength, measured in nanometers, or as energy particle measured in kilo-electron volt. The X-ray region on the electromagnetic spectrum overlaps with the low-energy gamma rays range and the high-energy ultraviolet range. Only a small portion of the X-ray spectrum range is used for XRF spectrometry. X-rays can occur as a continuous spectra or as characteristic line spectra. Let's refresh our memories on some basic chemistry terminology. An atom consists of a nucleus made up of protons and neutrons, as well as orbitals or shells filled with electrons. The orbitals that surround the nucleus and where the electrons are hosted are labeled K, L, and M, with the K orbital being the closest to the nucleus. The mentioned properties of X-rays can come into play through various ways when X-rays interact with matter, in this scenario being a sample of any material type. The atoms in a sample will produce X-rays when irradiated by X-ray photons of sufficient energy. The X-ray photons can be sourced from an X-ray tube, for example, as a primary beam directed onto the sample. The X-rays produced from the atoms of the sample are called secondary X-rays or fluorescent X-rays. Each element in the sample excited by primary X-ray photons will produce X-rays that is distinctively characteristic of the element. Due to the fact that the X-rays can be transmitted, reflected, diffracted, scattered, or undergo photoelectric absorption, they are subject to matrix effects. We will review this term a bit later in the presentation. But it is important to note so far that due to these matrix effects, the intensities of the X-rays produced are not directly proportional to the element concentration in the sample. Let's have a closer look. An element's characteristic line spectrum is produced when an electron or X-ray photon interacts with an electron in the atom of a sample. The electron is removed from its orbital and in return creates a vacancy for an electron in the inner orbital shell. Since the atom is now in an excited state and unstable, it naturally wishes to fill the vacancy with an electron from an outer shell of the atom. An electron from an outer orbital or shell of the atom fills the vacant space and in return generates an X-ray photon. It is important to note that this electron transition can only occur if the electron has sufficient energy to remove electrons from the inner orbital. Since the nucleus is positively charged and the electrons negatively charged, the electrons are attracted to the nucleus. The closer the shell with electrons is to the nucleus, the more attracted the electrons are to the nucleus. It is described as having a high binding energy. It is more difficult to remove electrons in shells close to the nucleus than other electrons shells further away. In spectral terms, a K shell electron will have a higher binding energy than an L or M shell electron. More energy is needed to eject an electron from the K shell than to eject an electron from the L or M shell. This is of course a simplified interaction of an electron or X-ray with an atom to produce characteristic line spectra. Electrons can also be scattered. Applying this concept to the XRF spectrometer, the primary X-rays produced from the X-ray tube will interact with atoms from the sample to emit secondary or fluorescent X-rays. The emission of the fluorescent X-rays will produce a characteristic line spectrum, as mentioned previously. This line spectrum will allow for the determination of chemical composition of the sample. X-rays can also interact with atoms in the samples by absorption and scattering in either an elastic or inelastic manner. These interactions will need to be addressed and compensated for. Here is a diagram to explain the annotation of a characteristic line spectra. When an electron vacancy is filled by an electron in the L shell, it is indicated as a K alpha line. When a similar transition occurs between M shell electrons and K shells, it will produce a K beta line or a L alpha or L beta line if the interaction is between the M shell and the L shell. In XRF analysis, only K alpha lines are generated for low atomic numbers, from beryllium to potassium, because no higher electron shells are available. K, L, and M lines are produced by medium atomic number elements, from calcium to sulfur. For higher atomic numbers up to uranium, only L and M lines can be produced, as an XRF X-ray tube can only produce a certain amount of energy and lack to efficiently excite K shell lines from these elements. So generally speaking, the higher the atomic number of the element, the higher the energy of the X-rays. The number of possible X-ray emission lines also increases with the increase in atomic number, because more electrons are available. With a better understanding of the physics of XRF analysis, let's take a more detailed look at the spectrometers. Two types of XRF spectrometers are available, either an energy dispersive ED-XRF or wavelength dispersive WD-XRF. In this course, we will only briefly discuss the EDX spectrometer, as at our laboratory we use a WD-XRF spectrometer from Analytical. The EDX is usually smaller than the WDX. It can measure all elements simultaneously and use a special X-ray detector that gives a distribution of voltage pulses proportional to the energy of the electron photons. The EDX instruments can range from a rather large floor-standing instrument to a small, more compact benchtop instrument. A compact handheld instrument is also available, which serves as a very convenient, quick screening tool. The wavelength dispersive instrument may be either sequential, simultaneous, or a combination of both. The sequential instrument measures one element at a time, whereas the simultaneous instrument can measure all elements at the same time. For this, a separate measurement channel is required for each element. At our SAF laboratory, we have a sequential wavelength dispersive XRF. So let's take a more detailed look at the different components with this instrument. This diagram shows the layout of a sequential WD XRF. It consists of an X-ray tube, primary filters, a sample cup and loading port, a collimator mask, up to 4 collimators, up to 8 analyzing crystals, and 2 or 3 X-ray detectors. For solid samples, the spectrometer is kept under a vacuum to minimize absorption of X-rays in the X-ray path from the sample to the detector. For liquid or loose powder samples, the vacuum may be replaced by helium or nitrogen path. So let's start with the X-ray tube. The X-ray tube is the primary source of X-rays that is needed to excite the atoms in the sample. So how does an X-ray tube create primary X-rays? A current is applied to the filament in the tube. A potential difference is then created between the filament and the anode, where the electron is attracted to the anode and creates ionization of the anode material. The ionization is the creation of an electron vacancy, which in return is followed by the emission of a photon electron. The electron vacancy is filled and a primary X-ray is emitted. A variety of X-ray tubes are available. The correct choice of an X-ray tube will depend on the tube design, the choice of anode material, that is usually rhodium, but can be molybdenum, gold, tungsten, copper, chrome, or scandium. Other factors, such as the thickness of the beryllium tube window, kilovolts and milliamp settings, cooling, and primary beam filters, will also contribute to choosing the correct settings to optimally excite the sample. Primary beam filters are used mainly to remove interference lines from the tube, improve the signal to background ratio, giving low detection limits, and better counting statistics for trace elements. It is also used to suppress spectral impurities from the tube spectrum. Next, we follow the X-rays emitted from the sample down the optical path of the spectrometer. This includes the collimator and its mask, as well as the analyzing crystals. The collimators and the collimator mask is used to allow only radiation received from the sample to pass through the collimators, diverting the radiation to pass through the collimator slits in the straight parallel beams. The spectrometer can be fitted with a fine, medium, and/or coarse collimator. The radiation beam from the sample is directed by the collimator onto the analyzing crystals, which in turn disperse the X-rays according to Bragg's law. A number of crystals are used to cover a wide range of wavelengths. The lithium fluoride crystal range is useful for very short to medium wavelengths, which include elements from nickel to uranium. The germanium crystal is used for phosphorus, sulfur, and chloride. Thallium acid phthalate crystal is used for magnesium, sodium, fluoride, and oxygen. Of course, the crystal in itself can also be excited by X-ray radiation, and can emit their own characteristic spectral lines. These X-rays will be seen by the detector and will form part of background noise. This is known as crystal fluorescence and should be corrected for. As mentioned before, wavelength dispersive XRF is based on Bragg's law, which allows for the diffraction of X-rays by the analyzing crystals and in return determine the signal of each element, one element at a time. Three factors play an important role in the intensity and dispersion of X-rays in the optical path. They are angular dispersion, resolution, and sensitivity. The angular dispersion depends on the type of analyzing crystal being used. The resolution depends on the spacing of the collimator slits, the choice of analyzing crystal, and the reflective properties of the crystal. The sensitivity, expressed as count rate per unit concentration, depends on the reflective efficiency of the crystal and the choice of collimator slit. It is important to remember that the sensitivity can be increased, but at the expense of the resolution and vice versa. The last component of the spectrometer to be discussed is the detector. The detector converts the X-ray photons diverted from the analyzing crystals into measurable voltage pulses. The spectrometer is fitted with two detectors to cover the necessary wavelength range. A scintillation detector is used for short wavelengths or high energies, and a gas flow detector, also known as a flow counter detector, is used for longer wavelengths or lower energies. A sealed gas detector can also be mounted in the spectrometer, which is useful for intermediate wavelengths and energies. The voltage pulse produced from the detector is converted into a pulse height distribution plot, or PHD. Pulse height selection is carried out as a filter to remove any unwanted noise from a low voltage noise, high order reflections from analyzing crystals, crystal fluorescence, and escape peaks. Escape peaks occur from the excitation of gas atoms in a gas-filled detector. All the discussed components are used when an analytical program or application is set up. For each channel or characteristic line to be measured, the following selections must be made. What X-ray tube is available in the spectrometer, and does it allow for enough excitation for the elements of interest? Use the optimal kilowatt or milliamp settings for the tube. Decide on whether it is necessary to use a primary beam filter or not. What sample cup material and size is necessary to be used? This will depend on your sample preparation. What collimator and collimator masks should be used? Very fine, fine, medium or coarse. What analytical crystal will be best for the specific elemental line? Remember to keep in mind the resolution and sensitivity of each line during the selection of collimator and crystal selection. Choose the best detector to use. Clean the noise with pulse height selections, and then establish appropriate counting times on the peaks and backgrounds if needed. XRF analysis can be done on a variety of samples, from solid samples to liquids, inorganic or organic material. At our lab, we generally analyze any glass material. At our lab, we generally analyze glass materials, raw materials including sand, limestone, dolomites, refractory slags, and then we can do complete whole rock analysis on any type of rock sample for major and trace elements analysis. We also often do cements and soil sediments and sludges. The sample preparation, of course, depends on the type of sample and on the elements that the client wishes to be analyzed. Sample preparation is crucial for good, meaningful XRF analysis because of matrix effects. Let's have a look at the sample preparation methods. The preparation of samples for XRF analysis can be done by two methods. The first is by making a fusion disk from your sample or a pressed powder pellet. The decision as to which method to follow will depend on the elements to be analyzed and the estimated concentrations thereof. To make either a fused disk or a pressed powder pellet, the sample needs to be milled in a fine powder form. If it is not in a powder form, it will have to be crushed, milled and dried, as would be the case with rock samples. It is important to note that the main objective of this is to reduce the particle size and homogenize the samples, all in the attempt to reduce mineralogical effects. Detailed XRF sample preparation is discussed in our ICP, XRF and CHNS sample preparation course. Please have a look at this for more information on correct sample prep. After the preparation of either fused bead or pressed powder pellet, analysis can occur. The disc or pellet is placed inside the sample cup, which in turn is placed into the XRF spectrometer for analysis. With correct storage conditions, fused beads and pressed powder pellets can be used multiple times. It is thus a non-destructive technique. After we set up an analytical program or application with the appropriate selection of spectrometry components, we will need to calibrate before analysis can occur. Unfortunately, calibration in XRF is not an easy task and is time-consuming to provide good quality calibrations. But once a calibration setup is completed, it only requires recalibration once a year, more or less, with the use of a drift monitor correction. Factors that can affect calibration are the background, spectral overlap, and matrix effects. The background is dependent on the sample composition. Spectral line overlaps occur when an element is present at the same peak of the analyte of interest and contributes to the background of the analytical peak. Matrix effects consist of absorption and enhancement of X-rays and particle size and mineralogical effects. These matrix effects can cause the increase of excitation on characteristical lines or reduce the excitation. These matrix effects can cause the increase of excitation on characteristical lines or reduce the excitation, with both scenarios leading to the incorrect representation of the analyte's line spectra. Matrix effects can introduce up to 300% error to the quantitative data, so it is essential that it must be corrected for. To correct for matrix effects, we must calibrate the instrument with standards that are similar to the sample type. Matrix correction can also be applied by a variety of correction models, which will correct for the absorption and enhancement of analyte lines. Particle size and mineralogical effect can also be eliminated with correct sample preparation of a finely milled sample, matrix matching the sample and the standards used in the calibration, and using fused beads. Once a corrected, good calibration curve is established, where the measured intensities of each element for a number of standards are plotted against their concentrations, an unknown sample can be measured where the concentration for each element is read off the calibration curve. The displayed data set show the results of major oxide concentrations of 3 standards, with the loss and ignition determined as well. XRF results should fall between 98 to 102 weight percentage when all the elements are accounted for, including the volatiles, which is the LOI, loss and ignition. Results lower than 98% may be related to bad sample preparation or bad analysis. It could also be possible that the major element was not analyzed. Bad sample preparation can introduce up to 100% error on the results. The following images displays a partial portion of a line spectrum from an unknown sample. The line spectra can be used as a qualitative analysis to determine what elements are present in the sample. To conclude, let's summarize the analytical abilities of the XRF spectrometer. XRF spectrometry is a non-destructive analytical technique. A wide range of material can be analyzed, such as solids, powders, and even liquids. The XRF spectrometer can be applied for qualitative and quantitative analysis. It can also be applied to a wide range of concentrations, from 0.1 ppm to 100%. Wavelength dispersive XRF spectrometer can analyze from fluorine to uranium. It requires minimal sample preparation and can produce very precise data. First-time calibration setup can be difficult, but it is easy to maintain. XRF analysis is not very suitable for ultra-trace element analysis, but a TXRF can give very low limits of detection, or ICP-MS analysis technique can be used. It cannot analyze hydrogen, helium, or lithium. It does not analyze light elements at low levels very well. It has a poor sensitivity for beryllium, boron, carbon, nitrogen, and oxygen. The analysis can be slow with long analytical times, especially for a large number of trace elements. Different matrices require separate calibrations, and a skilled operator is required to produce reliable results. From myself at the XRF unit, I would like to thank you for your time. I hope you enjoyed the session and gained additional knowledge into the basics of XRF analysis. If you have any questions, you are welcome to contact me for guidance. For more information on Central Analytical Facilities, please visit the SAF website and like the Facebook page. For weekly info on our ICP XRF unit, please check out our LinkedIn page. We wish you all the best for your work ahead.